Today, I want to finish off what we started before you went on your vacation, and that is capacitors and circuits. The only thing you're going to be turning in today is a picture of your notes so that I can see that you picked up on all the main ideas that we talked about. Okay, so a quick review, since it's been a while since you've been thinking about physics. Capacitors are designed to store charge, energy, and create fields. You measure the quality of the capacitor based in farads. It is dependent upon the area of the plate that's going to store the negative charges. That's going to be in meters squared. The material of the insulator, and the distance between the plates. That should be, of course, measured in meters. We looked at how capacitors charge, with one side picking up negatives from the battery and pushing negatives off of the other plate to create a positive plate. The positive plate then pulls more negatives onto the first plate until the capacitor has reached full charge for that particular voltage. We also looked at discharging the capacitor, and we saw the formulas for the amount of charge stored on the capacitor, the energy stored on the capacitor, and the strength of the electric field created by the capacitor. We eventually will be looking at the electric field when we turn capacitors into particle accelerators and particle deflectors for some pretty high-tech equipment. Okay, we also want to look at capacitors in circuits with resistors. These are called RC circuits. We did a lab where we looked at the discharging of a capacitor, but we started by charging the capacitor. We hooked it up directly to a battery. The only resistance that was in the circuit was from the battery and maybe a little bit from the wires. This resistance was so small that the capacitor should be fully charged in just a matter of seconds. We then discharged our capacitor through a resistor, and we watched how the voltage on the capacitor and resistor dropped as time progressed. We saw that it formed an exponential decay graph, just like our nuclear half-life. The equation was quite similar. We have the voltage at any given time is equal to the original voltage, and then we had the E raised to the decay constant. In this case, the decay constant depends on the resistor and the capacitor that are used in the circuit. We can do half-life just like we did with radioactive decay. We look at our starting voltage, and then we find out how much time is required to get us to half of that starting voltage. We would never want to describe how much time goes by before it's fully discharged, because it technically never fully discharges. It asymptotically approaches zero. Now, for all practical purposes, the voltage will become so low that we can call it zero, but technically, it never truly hits zero. We then had our capacitor discharged not just through a resistor, but also through an LED. And we watch when we do this, we take the battery off, and now the LED is lit up solely by the capacitor. And we see how it slowly fades away as the voltage on our capacitor heads toward zero. We see that the time it takes for the capacitor to discharge is determined by the resistor that we use in our circuit. More resistance is going to mean it takes more time for the capacitor to discharge. I'd now like you to sketch out, not quite yet, the process of discharging our capacitor. So we start with a battery in our circuit, and then we're going to remove the battery and start the discharge process. This is the circuit I'd like you to draw. Show the charges on the different plates of your capacitor, show the direction of current flow, and describe how the current is dropping, the charge on the capacitor is dropping, the voltage on the capacitor is dropping, and the voltage on the resistor are all dropping as time goes on. Now, the two important parts are the initial conditions and the final conditions of this circuit. So initially, we have our capacitor fully charged at 8 volts, fully charged at 400 microcoulombs, and when we throw the switch, we get a certain current. I'd like you to realize you can predict that current by doing the voltage divided by the resistance. So in this case, we would use 8 volts and 900 ohms. We would get a value of around 9 milliamps. Realize that current is the original current and it's going to begin dropping immediately. The final condition, again, it technically never reaches this final state, but for all practical purposes, it gets there pretty quick. We have no current, our voltages have dropped to 0, and our capacitor is fully discharged. Our capacitor now has 2 neutral plates, just like it started out before we charged it. When we look at these graphically, we would see our current dropping. It would have a y-intercept of the original current. And like I said, we can find that by doing the original voltage divided by resistance. The charge on the capacitor will have the same graph, and the original charge should be equal to the capacitor value times the original voltage. The voltage graph looks just like what we collected in lab. Again, exponential decay with a y-intercept of the original voltage, which is probably going to be equal to the voltage of the battery that was originally used to charge the capacitor. Okay, we now want to look at the graphs for charging and the circuit for charging, and this is going to be a little more complicated. So again, start with a picture. Notice the capacitor is totally discharged. It has no charge, no voltage. We have an 8-volt battery, and our switch is open, so nothing is happening in our circuit. When we close the switch, we're going to get a flow of current through our circuit. Initially, the capacitor offers no opposition to the flow of electricity, and we can find the initial current the same way we did before. We take the original voltage, which would be the battery voltage, and we would divide by our resistance, so in this case, 900. However, as soon as we start getting charges building up on the capacitor, it's going to slow down the flow of electrons. So even though we haven't added any resistance to our circuit, we're going to get less current because the voltage on the resistor would be the battery voltage minus whatever voltage has developed on the capacitor. Okay, so when we watch this happen, we can see the current dropping over time. We can see the voltage on the capacitor going up, the charge on the capacitor going up, the voltage on the resistor going down. And again, the current is going down. All right, again, it will never fully charge, but it will get close enough that to 3 decimal places, it will reach 8 volts. So initially, when we first close the switch, we have an original current, which we can find with battery voltage divided by resistance. We have no charge and no voltage on the capacitor, and we have the full battery voltage on the resistor. This is not going to last long as charges will start to accumulate. The charge on the capacitor will go up, the voltage on the capacitor will go up, and the voltage on the resistor will go down. Hopefully you realize that the voltage on the capacitor plus the voltage on the resistor must always equal 8 volts. The charge on the capacitor can always be found by the capacitance value and the voltage on the capacitor at that given moment in time. Once the capacitor has fully charged, again, it never fully charges, but it gets closer and closer to this state. All 8 volts will be on the capacitor, no voltage will be left on the resistor, and there will be no charge flowing through the circuit. The charge on the capacitor will equal the capacitor times the voltage of the battery as its final charge. If we look at these graphically, the current graph would look just like it did before. The charge graph, however, would look much different. It would start with no charge on the capacitor, and it would increase rapidly and then begin to drop off and asymptotically approach the final value for the charge on the capacitor. Finally, the voltage, we're going to have 3 different lines. If we're talking about the voltage of the battery, that's going to be a constant. If we're talking about the voltage on the capacitor, that's going to mirror the charge on the capacitor. And if we're talking about the voltage on the resistor, it's going to be our classic exponential decay. The spot where the 2 graphs meet will be our half-life, and this will be when we have our resistor at half the original voltage. Our capacitor is going to be halfway charged. All right, tomorrow we're going to look at some configurations, and I'm going to have you do a few math problems. For today's grade, all you have to do is turn into Google Classroom a picture of your notes.